this class as well. I did change my image.
Oh.
So I refreshed my image. It's possible there's a corruption, but I'm not 100% sure.
Is there maybe a bad sector like on the SSD or something?
That would be reported too, so I'm not really sure what happened.
Oh, okay.
Okay. So we're gonna get started, and I know some people are gonna stream in later. So what I'll do is I'm gonna waste some time to talk about MBTI, the Myers-Briggs Personality Type Indicator. But this one is particularly interesting. I'm not sure how many of you actually read this stuff here, like taking a class from TAC. Okay, I guess none of you did. Okay, so depending on your personality type, taking a class from me can be a very different experience. Okay, some people may experience in one way, and some people may experience it in an entirely opposite way. So, but this one is kind of fun. Okay, this is definitely not required. I'm not going to quiz you on these things. So what they do is they assign these personality types to well-known shows. So here's the Game of Thrones, which I don't watch, okay, so I cannot identify with these particular characters. The Little Ponies, okay, so, and then we have the Lord of the Rings, and then we have Profile of a Survivor, Harry Potter, of course, Disney Princesses, Grey's Anatomy, and Marvel Comics. And this is kind of interesting. They got multiple. They have 4 of those characters per category of personality indicator. So, well, I'm putting this up, just so that to encourage you guys to kind of find your type, and and of course there's Star Wars as well, Star Trek. Okay, this one I have to watch because I haven't watched this one. Okay, so who is our INTP? The Doctor. I don't know. The Doctor seems pretty J to me. He's pretty judging. It doesn't seem very perceiving to me. Data, on the other hand, seems a lot more perceiving than he's judging. So I think this may not be correct.
Yeah.
Yeah.
I agree with that.
Yeah. So anyway, just little fun stuff for you guys to explore when you have time to do it. So that being said and done, we're going to move on and continue to talk about propositional logic, CNF, proof by contradiction, and how we use resolution to prove theorems. Yes?
You're, I guess, releasing the grades for the exam, like one question at a time?
Well, one question at a time. I'm sorry, it is a little bit slow, but you can see that with a 2-point question, I got 4 parts, and each part has 5 grades. So that's how I grade each and every single of the 39 submissions. So it's going to take a little bit of time, but that's the process. So that is good. So did you guys download this file that I uploaded the other day?
I did.
Okay, so hopefully it is useful.
Yeah.
So we are getting back to propositional logic, but before we move any further, I want to point out the key items, basically the roadmap of what we are doing here, because it is easy to get lost in the pine needles and not really see the forest. So what I'm doing here is I'm going to let you know, basically to show you, what the entire forest looks like. Okay, so we got several major ingredients. We have propositional calculus or logic system, however you want to call that. So propositional calculus is really just a system to say, okay, these are the symbols in alpha, these are the operators in omega, these are the known to be true well-formed formulae in iota, and these are the transformations in zeta. Okay, and we just blindly apply those transformation rules to come up with more well-formed formulae that are known to be true from starting with iota. So that's the whole purpose of propositional calculus, is we are trying to formalize the application of logic and also just operations in general. It's all syntactic. So the importance of this is it's all syntactic, which means computers can do it really well. Okay, I'm going to put well in quotes here, okay? The reason why I put well in quotes is because the computer can match syntactic rules to existing well-formed formulae known to be true. Yes, that part can be done with exceptional speed and efficiency. But the problem is the computer doesn't know in which direction to take it. Okay, so with a propositional calculus system that is kind of like our Boolean algebra system, the computer can take this in the wrong direction and keep adding new known to be true well-formed formulae that is not going to contribute to the actual proof. Okay, and we don't know when to call it quit. We don't know when to say, okay, I think this particular theorem cannot be proven. Okay, do you wait 5 minutes? Do you wait 5 hours? Do you wait 5 weeks, 5 years, 5 centuries? We don't know. There's no guarantee of termination. Okay, so that's why propositional calculus by itself is interesting, but only from the philosophical perspective. So the next thing we talked about was CNF. Now CNF is interesting because conjunctive normal form has exactly the same expressive power as normal Boolean expressions. That is big because, so let me write it down here. Same expressive ability as regular, okay, I will put regular in quotes too, regular Boolean expressions. In other words, everything that you can express as a Boolean expression in C and C++, we can turn all of those into CNFs. And this is not a challenge to those of you who say, well, in that case, I'm going to turn all of my expressions, Boolean expressions in my C and C++, 400, 430, all the homework assignments into CNFs when I turn it in. Yep.
One thing I was a little confused on, when you have like the statement before you convert it into a CNF and then the actual form, do they have the same truth table? Or
they should.
Okay, that's what I wasn't sure if that was
true. We'll test that. Okay, so in today's class, we'll test whether that is the case or not.
Because I figured it was, but I think when I was first attempting the homework, I was getting it wrong initially, so that's why I was starting to doubt myself.
Okay, so but this is really interesting because CNF only involves the negation of variables. Okay, negation of variables. It has variables. You can throw constants into this, that's fine, or negation of constants and negations thereof, okay? And it has one single operator, okay, well, two. It has got disjunction of constants, negations thereof, variables, and negations thereof. And then you have conjunction of disjunctions. That's very, very structured. Compared to a general Boolean expression, a CNF is very, very structured. Is that okay? It seems to be very confining, but we know that it's not, because you can give me any Boolean expression and I can turn it into CNF. So CNF is like a canonical representation of general equations in Boolean algebra. So that's really cool. And then we have another ingredient to this pot, which is resolution. So resolution is a single transformation rule, okay, based on Boolean logic. It is a single transformation rule. So it's a transformation rule that only works on CNF. Because we're looking for two disjunctions where the one needs to have the non-negative version of a variable and the other one has the negative version of the same variable. As long as we can match that, then we can concatenate the two expressions, make a new one, and we toss away the variable where on one side it is negated, on the other side it is not negated. That's resolution. Okay? But then we also know that in resolution has one huge advantage over the other transformation rules. The result of a transformation using resolution is, what kind of property does it have? When it has one term fewer than what you start off with. Okay, so that's really, really useful. Okay, so the result a transformation has one fewer variable than what we start off with. Now that is big because this means you can only apply resolutions so many times. So either you get to a dead end where you can no longer apply resolution to get new results anymore. Okay, you can apply resolution, but you get back whatever you already have. Okay, which means you're not moving forward. Or you get to contradiction, where you go like, oh, okay, we have to stop here because false is a part of the well-known formulae to be true. I mean, that cannot be the case. I mean, that's you have a contradiction. So the other part of this, just looking at resolution, is it guarantees termination. Okay, you can no longer say, oh, P or not P is true. P or not P, or the negation of P or not P is also true. Take that thing and then say, or the negation of that thing, that is guaranteed to be true as well. You cannot make senseless and useless well-formed formulae using resolution. Every single time you apply resolution, you end up with something that has one term fewer than what you started with. So even if you start off with like 50 different variables, okay, you apply resolution once, you end up with 49. You apply it twice, you get 48, and so on. So eventually it will boil down to either the false, which is you get a contradiction, or you get to the point where you can no longer make new well-formed formulae that you have not derived already. So you have hit a dead end and it's time to stop. So this is really useful. It guarantees termination one way or another. So whether the theorem that you want to prove is a theorem or not, it will stop. But in order to apply resolution to prove something, we also need the last ingredient, which is proof by contradiction. So this is needed in order to use resolution as an engine of propositional calculus. So we do okay so far with the forest, basically how all of these concepts relate and why they're all kind of interrelated to do what we need to do. What we are interested in is theorem proving, okay? That's what we want to do. But in order to do it in a way that is mechanical, that guarantees termination, we need all of these ingredients. So is that okay so far with all of this stuff? Kind of? Okay, I'm going to keep this up, and then we go back to the notes, and then I'll point out, where, in the note we mentioned all of these things. So section 3, yeah, question? No, okay. So section 3 is only talking about general propositional logic, and it leads to certain problems. Even though it is useful, it is a very good formalization of how we apply logic. It has a problem because if you ask a machine to do this, we haven't really talked about completeness and soundness, just ignore that for now. But it has a problem because it can go endlessly, and the computer can basically just keep generating useless, well-formed formulae that is not getting you any closer to the theorem that you want to prove. So we talked about resolution, and the first thing we did with resolution is to prove that this implication is always true. Now this is the details of the steps are important as well, but I don't want to spend class time to talk about it, because we talked about it once already. Okay, so I'm not going to talk about it again unless there are specific questions. But the most important part is this implication. Let me highlight which one we are talking about. This implication is always true, which means if you have two expressions, they're both disjunctions of stuff, where one disjunction has a particular component and the other one has the negation of the same component. If you know this sub-expression is true and you know this sub-expression is true as well, that means this expression has to be true, which is the concatenation of the two sub-expressions, but tossing away the component where it is non-negated on one side and negated on the other side. This is generally true, okay? Psi does not even have to be a single variable in this case. Psi itself can be a huge sub-expression of some kind, okay? But the key is, whatever psi is on this side has to be the same side that is negated on the other side. That is the only requirement. Yep?
So this is an example of like 10 transformations that would be found to transform the original statement into the second statement.
This itself becomes a transformation because it is, now we know it is sound because we use Boolean algebra to prove it. So once you use Boolean algebra to prove that it is sound, it makes sense. If you turn it into a transformation rule, that means that transformation rule is grounded. There's a reason for that transformation rule to exist.
So if like a computer was going to try and evaluate whether that was true.
Whether what is true?
Whether the and statement implies this psi.
Well, that's why these have to be sub-expressions that are known to be true already. And you start off with stuff that you have in iota. Is that okay? So you started with stuff that you have in iota, and then the result of the resolution is put back into the pool of well-formed formulae known to be true. So those can once again be used in resolution for further resolutions. I'll show you an example later. So this is resolution, and this part proves that resolution works. Okay, it makes sense. We can derive the correctness, or we can prove the correctness of resolution using Boolean algebra. Yep.
I'm just confused with one of the steps there. The fourth to last one, where it starts with one and negation of psi. I'm just wondering how you went from that step to the next one.
Okay.
How'd you simplify that the one and
Because one and whatever is just the whatever. And then whatever and one is just the whatever two. In other words, I simplify this to this. I simplify that to just that. Because and one is analogous to multiplication by one in algebra. So it doesn't really change what the original value is because it is the identity of that particular operation. And you can prove it too by using a truth table. Okay, I think we might have done this before, but you can basically say, okay, this is x and true. Now, since we only have one single independent variable, it can be false or true. If x is false, x and true is false. If x is true, x and true is true as well. So these two columns are identical, which also means that x is equivalent to x and true. The and true doesn't do a single thing.
Oh, okay.
And because of this, we apply over here, so we can now simplify this entire thing to just not psi, and then we can simplify this entire expression to just psi itself.
Okay.
And because of these two grouped together, it's just true itself. So now we have true or blah blah blah, and it is just true. Yep.
Yeah, that part makes sense.
Okay. Cool. All right. So 5.1 is just proving that resolution makes sense. Okay. In terms of logic, well, if it makes sense in logic, we turn it into a transformation rule.
Can you talk about when you scroll up on the first statement?
On the first statement.
Yeah, like right there. On the very top line where it says on one side it'll be equal, and then on the right side it has so right there the double parentheses. And you applied the not all the way to the outside. Is that?
No, not all the way to the outside. This negation applies starting from here and it ends here.
Right. I thought the not supposed to apply to the first set of variables when something is implied.
Yes, but this entire thing is the first part.
Oh, so you keep it as a whole.
Yeah.
Gotcha.
Yeah. So I put conjunction has a higher priority compared to implication.
So it's implied that there's another set of parentheses inside that implies?
That is correct. Yep. So you can imagine there's one parenthesis open here, and it closes here.
Okay, that makes more sense.
Okay. I apologize, it was not clear. Yep. So implication usually has a lower priority compared to conjunction and disjunction. But that's good. That's good. Good for me to use this chance to clarify. Okay. So are there any questions about resolution itself and why, how it fits into the big picture so far? The questions? Okay. It is the big picture that we really want to deal with at this point. Okay, because if you once you know the big picture, the details would actually make sense a lot of times. Okay, so you might notice that in order for resolution to work, it relies on these two sub-expressions using ORs. And it ends up with another expression that also has an OR in it. Okay, so this means if phi, psi, okay, if phi and rho themselves are just disjunctions of something, and psi itself is just a variable, that means the format of what you start off with is going to match exactly the same format as what you end up with, because they're all just disjunctions of something. Okay, and that's why we want to get every single Boolean expression to be expressed as a CNF, because CNF enables the application of resolution. Let me say that one more time. CNF enables the application of resolution. And on top of that, you don't lose anything. You can convert any Boolean expression to CNF. So it has exactly the same expression ability as a general Boolean expression. Is that okay? All right, so in section 5.2, it is really just both a statement to state that you can convert any Boolean expression into CNF, and also giving you the clues of how to do that. Yes?
The 4 bullet points at the top are essentially what we're using in the homework, right?
Yep.
Right.
Yep. So what you do in your homework you look at the top level operator first, and you go like, okay, is it an AND, is it an OR is it a negation? Well, depending on what it is, pick whatever transformation that applies.
By top level, you mean outside, the furthest outside parentheses?
Top level means, okay, we can use the example to illustrate what top level means. Okay. But that's basically the quote-unquote instruction to convert any Boolean expression into a CNF. Okay. So we'll get to the details a little bit later, but I do want to point out the big picture items first. So we'll get back to example 5.2.1 later, and we can probably work on another example as well. So the next big item is proof by contradiction. So proof by contradiction itself has its own proof. Because, well, I mean, you cannot use a proof technique not knowing that the proof technique itself is found. So that's why we have a corollary, which is a kind of small theorem to begin with, and then we apply the small theorem to the bigger thing, to prove that proof by contradiction itself works. Is that okay so far? So what this means, okay, the conclusion is this part here. This is the real big conclusion, is if psi is representing everything that you know, that you can assume known to be true, stuff that is in iota, and phi is actually a theorem, okay, which means phi can be derived from everything that you have in psi. If that is true, then you can say that phi and non-phi has to imply false. Okay, so that's the last piece that we need in this entire thing, because using resolution, we can resolve to contradiction. Because when you have, okay, so let me show you why I said that. Okay, so let's say we have a disjunction here. Okay, I'm going to use plus to mean disjunction. Is that okay with you guys? Okay, so let's say we have P and not P. Okay. Well, obviously P and not P resolve to 0. But remember, we're dealing with resolution, which is syntactic. It doesn't just look at the meaning. It doesn't look at the meaning of anything. So what you can do is you can cheat a little bit and say that I'm just to put a plus 0 in each term. Plus 0 means or false, right? P or false is just P itself. Not P or false is just not P itself. right? But that makes it fit the format. It makes it fit the conjunctive normal form, format. So then I can use resolution to add a term. So the new term is going to be 0 plus 0 because it is the concatenation of the original two expressions, but with p and not p taken out because we kind of consume that in the process of the concatenation. But 0 plus 0 is just 0. False or false is just false. So now we have a contradiction. Okay, so this step is really just showing you that using resolution, we can resolve to false at some point. Okay, if P is actually, if the theorem that you want to prove is actually a theorem, you will eventually end up with false. Is that okay? So, getting back to the notes, this part is important too, because what we want to do is to express psi itself as a CNF. We also want to express not phi, or the negation of the theorem that you want to prove, also as a CNF. We are not converting phi itself into a CNF. We are converting the negation of phi into a CNF. When you start with a CNF and you have a conjunction with another CNF, guess what? The whole thing is a CNF. If the whole thing is a CNF, we can apply resolution. Now, we can apply resolutions only so many times because we can apply resolution until it can no longer produce new results, or we can stop when it comes to false. But either way, it has to stop. It has to stop within X many steps. We know the maximum number of steps that it can perform before it has to stop. Is that making any sense? Okay, all right. All right, so now that we know, the entire roadmap, okay, getting back to this text document here, this is the entire roadmap, okay, because eventually all we want to do is to prove theorems. We're using proof by contradiction, but proof by contradiction is a result of using resolution. But in order to use resolution in this case, we need two ingredients. We need CNF to represent all the known to be true expressions to begin with, everything in iota. We also need to use CNF to represent the negation of the theorem that we want to prove. We mix those two ingredients into one gigantic CNF, we perform resolution. If we can resolve to false, we have contradiction, then using proof by contradiction, we prove the theorem itself has to be true. So are we doing okay so far with the roadmap, the big items, not so much the details? Okay, so what is left to do is your homework, which is resolution. So we'll go ahead and look at this particular example. I said I would go back to this one, this example here. So what we'll do is I'm going to work on this. I'm going to use a document camera in this case because it makes it easier for me to identify which one is the top level applicator and what we're going to do with it. So I'm going to use my document camera. Capture device. Oh, it automatically selects the right one, so that's good. Got my pen. I might just buy one of those multi-color pens like those.
They're cheap and great.
Yeah, they make one that has 4 colors and also a pencil.
Oh yeah, they sell them in the bookstore even.
Oh, they do?
Yes.
Okay.
Yeah, they're a little pricey in the bookstore. They're like $7, but.
7?
Yeah, they're like $7 or $8 in the bookstore.
Oh, that's not too bad. Because
Yeah.
Amazon has one like that made by Pilot, and it's about $9. So.
Yeah, this is just big, but it gets the job done.
Mm-hmm. Well, you won't be very, you won't be heartbroken if you lose it.
Exactly. Hey, that's why cheap's better.
Yep. So I'm going to copy this expression first, not P, or the negation of R implies Q, and P not or T close. Okay, there we go. Okay, so we got this expression here, and the question first is, okay, row sheet. Yep. It's a very pacifying music box type of music. And of course, if you're in my next class,
You'll learn
the
about
term
music
music
box.
box may not be what you want to hear right now.
Yeah. I remember that.
All right, so at this point, what is the top level operator? It is not the negation, because the negation of P produces something that is consumed by another operator. What is the top operator at this point? You can forget about everything in parentheses, right? So you have to look at the top level. So the top level is going to be the OR, okay? To be more specific, we are talking about this OR here. This is the top level. Is that okay? So let's read what the notes has to say about this. So the note said right here, if the top operator is an OR, so we are matching this case here, then the entire expression phi is the disjunction of some psi I. Okay, we got psi 1 and psi 2 in this case. Okay, so let's break it up. So we got psi 1, this is psi 1 itself, and this one is psi 2. Is that okay? So I'm just matching the example to the notes here, and yep.
I'm a little confused. How do you know which one's the top level operator? Because I was thinking the negation in front of the row.
Well, negation has a very, very high priority. It only applies to whatever is right next to it.
Okay.
So that means there's an implicit pair of parentheses around this. Is that the source of the question?
Yeah, I think so.
Okay, so negation always has the top priority where, if you don't use parentheses, it just applies to whatever is right next to it.
Yeah.
Yep, but if you use parentheses, obviously you can group things and say, okay, we're negating that whole entire thing. Oh, gave you the wrong sheet of paper?
Well, that was with the roll sheet. I don't know if that's someone here or that's yours.
Oh, okay. Yeah, this is for the next class.
Oh, yeah.
Yep. For those of you who are curious, we're talking about this. That's my processor. That's my Blue toy processor. Okay, so now we break it up. Okay, so we use this particular thing. We break it into either psi 1 and psi 2. So then the next question is each one a WFF1? In other words, is each one either a single variable or the negation of a single variable? Well, let's check it out. Okay. Psi 1 matches that description. It is the negation of P, and P is a variable. Cool. But psi 2 is not. Psi 2 is a gigantic expression, with negation and conjunction and whatnot in it. Okay. So that means we go back to this instruction here and we say, well, oops, it doesn't fit this requirement. Well, if that is not the case, that means phi, the entire disjunction itself, is not well formed yet. What do we do then? Well, we take it apart. Okay? So we then take a look at this and go, for each I in 1 to 2 in this case, because we only got 2 components, if phi I is not well formed, it's not a WFF1, then we will perform these operations. Okay. So we look at the what we have here. This one is a WFF1 already because it is just the negation of a single variable. It meets that requirement. We don't have to do any further processing with this one. We just leave it alone. Psi 2, on the other hand, is what? What is the top operator of psi 2? The and, the conjunction, is the top operation. Okay. So if the and is the top operation, and it doesn't hurt to add one more pair of parentheses like that here, okay? So the and is the top operation. So we go back here and we say, oh, okay, so if it is not a negation of a conjunction or disjunction, so we do not apply De Morgan's law. Psi, it is a conjunction, we apply distribution. So what do we mean by distribution? So what we're going to do is we are distributing the not P over these 2 items. Okay. So we say, okay, the result is not P, and then since we're distributing it, so we have to say, and the negation of R implies Q Yep.
Your not P is on the other side of a disjunction. You're dealing with the stuff on the other side of the disjunction.
But that's what it's distributing over, I think.
If it's a conjunction.
Oh, this is applying to the side itself. Okay, never mind. So we keep this one, and then we take side 2, and then we try to apply the distribution. So right now we can apply a little bit of distribution because we have P or T on this side, and then we can distribute it here. So I'm going to defer the application of, well, okay, we'll go ahead and do that. So we'll say this is P or T, and oh, it's the other way. It's P and the negation of R implies Q, and then we have an OR with P, oops, T, and the same thing. 1, 2, 3. There we go. So side 2 is now this. Sorry? Okay. So are we still doing okay so far with this? So we have done one iteration of new application. Yep.
I was wondering what it says on the right side there. Is that P, T, what?
That's a T. I crossed out the P.
Oh, okay.
Yeah, so this P is crossed out. Question?
Same question.
Same question? Okay. Okay, so the next operation is to go back to the beginning, and we ask the same question. What is the top level operator? So now, when you combine the whole thing, we'll combine the entire thing again. So we have not P that we have originally, and then we have the OR, and then we have P and the negation of R implies Q, close, 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 and then we have another OR of T and the negation of R implies Q, close, close, close. All right, so when you look at this thing, when you look at this particular expression, what is the top operator? It is still an OR. Okay, so we go back to the notes here, and we say we will still be applying this rule here, and we'll break it down into side 1, side 2, and side 3. So now when you go back to here, this is side 1, and side 1 is done already, and we don't have to do it anymore. This is side 2, and this is side 3. Is that okay? So for each one, we ask, is it already a WFF1? Well, side 1 is a WFF1. We know that from last time already. Side 2 is not a WFF1 because it is not a single variable or the negation thereof. And side 3 definitely is not either because it has the same format as side 2. Hey, so since they're not like that, what we do is we apply, it's not a negation. Each side is not a negation. That's not the top level operation. So it is a conjunction, and as a result, we want to apply distribution law. But this time, we have to change it a little bit first because we have a. You cannot distribute P over the negation of R implies Q unless you have processed that part already. So now you have to look at this part, and you say, okay, what can we do about side 2? P and, so we have a negation on the outside. Let's leave it alone for now. And what we do is we deal with the implication first. Implication becomes not the first one or the second one. And then we can do the same thing with side 3. So it is just exactly the same thing, the negation of not R or Q. So is that okay so far? It's the definition of implication. So after you apply the definition of implication, then you can perform the next level of operation, because we still cannot apply distribution at this point. So you have to apply the negation to the disjunction. The negation of a disjunction can be processed as using De Morgan's law. So now we have P and then you apply De Morgan's law. It becomes not R and Q. Okay, put the whole thing in parentheses. And then the second one is T, huh? Oh, not Q. Thank you. And then this one is not R and not Q. Close, close.
It should be. Oh, okay. Negation flips the operator from or to the end.
Yep. So that's De Morgan's law. But after you apply De Morgan's law, you can say, oh, this is just R itself, and this one is just not Q. And using the associative law of conjunction, you can just kind of dissolve the inner parentheses because it doesn't really make any difference. So the same thing over here, like so. Okay? So now we can see that, oh, okay, so this is a whole bunch of conjunction, and this is a whole bunch of conjunction as well. Okay? And then what do? Reduce distribution. Okay, so when we go back here, let me see if these still apply. So we have a disjunction on the top. Disjunction on the top, we do not meet this requirement. And then over here we have conjunction. We apply distribution law at this point. So distribution basically means, okay, we look at this whole thing and then we say, okay, let's do this. So it becomes a gigantic thing.
Yeah.
Let me kind of scroll up a little bit first. I need to make sure I get enough space to do this. Okay, so you have P or T and P or R and P or not Q. That's just distributing this P over these three terms. And then you have and. Well, you guys know what it's going to look like. So you have R or T and R or R and R or not Q, and then you have not Q or T and not Q or R and not Q or not Q. And that's all in one single gigantic conjunction. Okay? So that becomes your new phi. So you look at the notes, you go like, okay, we have a new phi, and the phi is still a disjunction, but it only has two terms, where one term is a big, huge conjunction. So you apply distribution again. Now you can simplify first if you want to. Okay, simplification is taking care of this one. You'll just say this is R by itself. Taking care of this one, say that this is not Q by itself. Those are the only two simplifications that we can do. All right, so now we have one last distribution to do, which is distributing this entire thing over the not P, which is at the beginning. So let me move things around a little bit here. Okay. So now we apply the not P. So for each one of these, you just say, not P or, not P. Yeah, go ahead.
Since R is on its own, can you get rid of R or T?
Oh yeah, this is and this. So we have a whole bunch of conjunctions here. So that means if R is here, the R or whatever can go away. So this can go away. This can go away. This can go away. And same thing with not Q. So this can go away. This can go away. And R makes this go away too. Wow, okay, so we can simplify the whole thing quite a bit. Thank you. That's a good idea to simplify before we distribute it one more time. So we have a not P on the outside, we have an OR, and then inside here we end up with P or T.
Why are we able to cross out the R's?
Okay, hold on a second. Let me do this first. And not Q. Okay. So the question is, how come we can cross out all of these terms? Okay, that's the question.
Yeah.
So to understand that part, I think we talked about this maybe a little bit last time too. Okay, so the idea is if you're dealing with, so we are dealing with two variables in this case, two independent variables. So we got x, y as independent variables. So we want to look at the expression x, let me think. Yeah, we want to look at the expression x, we want to look at the expression of x or y, and then we want to look at the expression of x and X or Y. Okay, so are there any questions about why these three columns are the ones that we, well, two to be more specific, why these two columns are the ones that we want to look at? How does this have anything to do with our simplification? Okay, let's switch back to the document camera. Okay. So in our document camera, you can see that my reasoning was to use this not Q to cancel out this one here, to make it go away, because this doesn't give me any extra information. But you can see how this is just a single expression itself. This is that single expression or something else. But I'm saying that this entire thing simplifies just to not Q. So getting back to the text editor, that's exactly what we have. That's exactly what we have here. We have x, which is our independent variable, and then we have x or y, which is one extra term, and then we have the conjunction of these two. So what we want to do is to show that this column, which is the same as this column here, is going to be the same as this column. The question is, does it work out? Okay. So we got 0, 0, 0, 1, 1, 0, and 1, 1 here. And obviously this one is just a copy of 0, 0, 1, 1. Okay. So not too much exciting things happening here. This is x or y, so you know this how this column should look like. It's 0, 1, 1, 1. And this column here, all the way over here, is the conjunction between this column and this column. 0 and 0 is a 0. 0 and 1 is a 0. 1 and 1 is a 1. 1 and 1 is a 1. Exactly. So this column is the same as x itself. So that's what we did when we did that simplification. Okay, so by using a truth table, this is how you can prove it. Okay. So with Boolean algebra, the nice thing is a lot of proofs can be done using truth tables. So are we good? Okay, all right. Sorry?
I'm explaining it logically.
Oh, okay. Yeah, you can also explain that logically too. But the truth table is kind of the cheat to do it easily. Yep.
So with that truth table applies to all the things that we canceled out on the previous page.
Yep. So in the document camera, we can do all the simplifications because this not Q is getting rid of this term. Anything that has a not Q or something, we can get rid of. So we can get rid of this, and this because of the not Q. Because of the R, we can get rid of this one, and also this one. So that's why we only got P or T left. We got not Q left, we got R left. Is that okay? Okay, so let's move on. So now we look at this one and we say, we have a conjunction here. So even though this one, this is still psi 1 is still good, but this is psi 2 is not good. And psi 2 has a conjunction as the top operation. It's a conjunction of a whole bunch of little items. So we apply distribution one more time, okay? So now this time we are distributing the not P over each one of these terms using, they will all be using conjunctions. So the application of distribution will now be not P, let's see, not P or T, this whole thing, and not P or R, and not P or not Q. Is that okay? All right. So now this is our new phi. Okay. If this is our new phi, we go back to the notes and say, okay, what do we do with this? It doesn't meet this requirement anymore. Top level operator is a disjunction. Nope, that's not the case. Top level operator is conjunction. Yep, it does work in this case. So in this case, if phi is a conjunction of some individual terms, we just break up the individual terms. Okay, it seems like we can do that. So now we break up all of these individual terms so that we just say that this is a set of well-formed formulae, and each one, the first one is not P or T. You can do the simplification first if you want to. But then the second item, which is an element of a set, is not P or R. And then the next one is not P or not Q. Just like that. That's our set of expression now. And then for each one, for each item in the set, we try to apply those rules again. Is that okay? So we look at the first one, and we say, if this is phi, okay, if we look at this one as phi, which category does it match in this entire instruction set? It matches the OR, right? Because the overall of the top level operation is an OR. So when the top operation is an OR, we say, okay, we'll look at phi as a disjunction of individual terms, where each individual term is psi 1, psi 2, psi 3. So getting back to the here, this one becomes our psi 1, psi 2, and psi 3. And then we ask the question, are these particular psis, psi 1, psi 2, and psi 3, are they, well, WFF1s? Are they either a variable or the negation thereof? Yep. Yeah. So that means this one is done. Okay, as a component of a CNF, it is done already. Then we move on to the second one and say, okay, let's pretend this one is phi. Okay, and if this is phi and the top level operation is an OR, so now we look at this one as psi 1 and this one as psi 2. Is psi 1 and are psi 1, psi 2 both LWFF1s? In other words, are they variables or negations thereof? Yep. Okay, so that meets that requirement. Now we move on to the last one and we say, how about this one? This is psi 1, this is psi 2. Ah, it works too. So now we're done. So we end up with a set of 3 disjunctions or 3 disjunctive expressions. But because everything in all the WFFs known to be true have an implicit conjunction to connect all of them, so now we have a quote-unquote CNF. Another way to express this is really the same thing. So this is the same way as that. These two are expressing the same thing. You first, and then you. Yeah, go ahead.
The first expression is just 1, isn't it? It's just one. Your first expression is just true, isn't it?
Yep.
Not P or P. Or
Yep, that is true. This one is just simplifying to 1. Yep. But since it's a conjunction with the rest, you can just take it out, and you will still be left with the other 2. Correct. Yep. Go ahead.
That's what I was saying.
Oh, the same thing? Okay. So in the end, we can say this can go away, this can go away, and we end up with these 2. So after all this derivation, okay, what we have shown is this big expression here boils down to the same thing as this expression here. And I think in my notes, it is slightly different. Darn it. What did I miss? There's a not Q or T here that is not in my in-class derivation. It's this one here, which is this one here. Sorry? Which is generated here. It's generated here. Okay, I think I know why. This not Q is supposed to be a not P. This Q here.
Oh yeah, I meant to tell you about that.
Yeah, so it's a typo. So if this is a P, then it would be canceled out and be absorbed by this term already. So that's my mistake.
I was so confused when I was reading that yesterday.
Sorry about that.
I meant to email you that last night.
Okay. Let me fix that first. So we'll fix it. Oops, the other one. Okay. And we are looking for example. think this is not it. Yep, here we go. And let's see, it's this fourth item from the bottom. So this is the last one. 2, 3, 4. So it should be this one. Yep, there we go. I see the Q here. So we'll change this to a P. So it becomes not P. So the next term becomes not Q.
Doesn't that affect the ones below it also?
Yeah, that's not the one.
What's
Okay.
Not Q or T.
Okay, I think we're going up a few more steps here. This one.
It's the fourth from the end.
Yeah, but it doesn't round the same way over here.
Oh yeah.
So this is the P over here, and as a result, when we simplify, we can get rid of that one. So this one can be. So we can make that go away here. There we go. And then when that goes away here, it will go away here too. That goes away here, it would go away here. There we go.
It actually cuts off that line on the when you print it. That last line, the really long one, it cuts off the last term when you print it.
Did you print it as PDF or HTML? That was
Oh,
his
sorry.
question.
No, it was the No, it was the PDF I printed.
Okay.
Oh, it's because it's in PDF
I
format.
think the PDF comes on.
Oh, okay.
Yeah, the PDF, is confining it to a letter size paper, with a certain dimension. But when you look at the HTML version, you can scroll as far as you need.
Oh, of course.
Yeah, so that's the reason why it's not going to be here. So, okay, I think I got it fixed. There we go. Okay, so it's good to reconcile the differences, because that was bugging me. It's like, how come it's different? Okay, but now that I fixed my notes, now the question is there's still an outstanding question of, is this really the same thing as this, the last one? How do we know? How can you prove it? Because it looks like the whole term T is gone entirely. I mean, how can that be? The term T seems useless, completely useless. Okay? So you can use a truth table. But how big is this particular truth table? It's a little bit bigger, right? This one has got, let's see, 1, 2, 3, 4 independent variables. So that means you have 16 items in this particular table. So if you were to test whether, the first expression, the general Boolean expression, is really the same as what we derived in the end, how would you do that? I wouldn't do it by hand. If I say you can do it by any means, but it has to be original, it has to be your way of doing things, how would you do it? Okay, this is how I would do it.
Are you going to do a spreadsheet?
Yep, spreadsheet. I'm well known for abusing spreadsheets, and this is one of those occasions. So you would say, but how do you use a spreadsheet to do something like this? Well, I don't know yet, because this is the first time I've done it, doing it. So we'll go ahead and figure this out. So we got P. Okay, there are several ways to do this. Okay, you can either use a number or you can use the kind of more manual method. So I'm going to use a number method because it's just a lot easier in the long run, even though it's quick and easy to type the numbers in. So let's get rid of this. This is 0. This is whatever the previous row has plus 1. Okay, 0 to 15. What is 15 as a binary number? 15 turns out to be 8 plus 4 plus 2 plus 1. That will make it 1, 1, 1, 1. If you are to use 4 bits to represent 0, what would that look like? 0, 0, 0, 0. Don't you think we need one row that starts with all zeros and the last row should end up with all the ones? Okay, so how do we extract the individual ones? So this is P, Q, R, S. Oh, we don't have S, we just have T. Okay, so how do we extract each one? How do you know which one? How do you know whether P should be a 0 or 1? Using our usual way of doing things. There's a general equation to do this. Okay, so you say we need this number. Okay, let me see. It's a division followed by a mod. So we have to perform a integer division first. Okay, that's just divide. Is divide integer division or is it not integer division? We can always take the floor of something. That's easy. So we will take this number and then divide it by. I got this equation in cisp 310, so I'm just trying to recall that. I think it's with this one it's by 8. Yep, there we go. So it's do this division by 8, and then we take the floor of this one, and then we perform a mod with 2, which is the base of this entire thing. True, false. Okay, so let's check this out. Does it work? Woohoo! Does work. All right, so we will copy this equation over here, but we have to change. Oh, okay. We have to change this back to A, and we'll change this to $A, which means when I copy it to the other one, it won't change the reference of the column. So this one becomes 4, and let's check it out. Yep, that's what we want. And then we copy over here. We change the division by 4 to division by 2. We got the alternating ones, almost alternating ones. And then we copy it one more time over here. This is now dividing by 1. I know division by 1 doesn't make any sense, but that's the general equation. So this way, so I know some of you would maybe saying, I can type really fast. By the time you figure out the equation thing, I'm done with typing already. What if we end up with like 8 independent variables? Do you think this method would be a little bit faster than typing all a table of 256 zeros and ones in that case? No, I take it back. With 8 independent variables, you have 256 rows, where each row has 8 individual bits. So you have 256 times 8 digits to deal with. So are we okay so far with this? Okay. Now, the other thing that, yeah, go ahead.
You're going to put this on?
Yeah, I can share that. Yep. Okay, so the 0 is really, it doesn't work that well, with conditional statements. In other words, if I were to put an and here between this one and this one, it may not like it. I don't know whether it knows 0 is false. Okay, okay, cool. That is good. Okay, because I was thinking, do I need to cast the type explicitly so that the spreadsheet knows what to do with it. So I'm going to do some stuff here. I will hide this column because it really serves no purpose other than generating this table here. And then we'll start to enter the equation. So the equation starts off with a not P. So we'll say, oops, not here. Although over here we can say this is not P or T. Okay, I forgot one parenthesis here. This is just for documentation, so I know what I'm dealing with. Okay, so we have an AND with. Oh, okay. Take it back. This is the negation of R implies Q. And P or T. There we go. Okay, so right here, we're going to enter this whole thing, using all those variables. So the first one is just the negation, the not of P. Yep.
Use the dollar.
Should we have parentheses
Hmm?
For not P implies.
And then we need something else here. We need another OR. So, and then the second component of the OR is, I know this is really hard to see. There we go. Okay, there we go. So the second component of the OR would be this entire side. So that entire side ends up with an AND. I have to read the operation in an infix with a prefix order, so this way it works better. So now we convert the convert the implication into a disjunction, and it would be the negation of R, not, and R is this column, and that will be ORed with Q, which is this column. Okay. And I think I'm missing a not. Yep, I'm missing a not because there should be a not on top of this. Okay. And then we have a P or T on the other side. So this P is this guy, and then T is this guy here. Close, close, close. There we go. Okay, let's do a spot check. Okay, just do a spot check of, let's pick this one. Okay. So does it match? Because P is true, so not P is false, so now we have to rely on the other side. R implies Q is false. Not false is true. P or T is true, so we have true and true, so that works out. Is that okay? All right. I'm just doing some spot checking here, not detailed. Okay, so this side here will be the actual equation that we end up with. Okay, so this is basically looking at, oh, not this one. We're looking at these two. Okay, which is also in the notes itself because I fixed the notes, so it's now correct. Yep, go ahead.
Shouldn't the one above it evaluate false?
Which one?
On the spreadsheet, the one above the one you just looked at, 12.
Row 12, this one?
Yeah.
Okay. Why would it evaluate to false? Okay, so let's check.
No.
So not P is
0.
false, so we need to rely on the other side. Yeah. So R implies Q. R implies Q is false. Not false is true. And then P or T. P or T is true. So we got true and true. So we have true and true or false, which is true. Looks right to me. Yep. Okay, so now we enter the other one. So I'm going to put it here. You know, this is this is the CNF. This is the conjunctive normal form. So we got not P or R, and not P or not Q. There we go. So now we have to put this all into that expression. We have an AND overall, or as the individual component, and then we have a negation of P and R by itself. So here's R, and then we have another OR that has not P as the first one, and then not Q as the second one. Okay, close all of those. And here's the moment of truth, no pun intended. Did they all match up? So I'm so lazy, I don't even want to do that. So I'm gonna say that's okay. Can you do comparison? I'm guessing you can do comparison. Okay, so it can't do comparison. Good. But I think I got the wrong row. Yep, off by 1. Okay, fine. Fine. Yeah. Okay, there we go. Okay, but when you have 256 rows, I don't even want to do this myself. So I would just say, equals to and with
Make sure they're all.
all of these. And it is all true. Okay, we're done. We're done now. But the idea is use the tools, okay? Don't do it by hand when you have tools that can help you, okay? And you can see that even a spreadsheet, a very humble application, like a spreadsheet, can be very useful if you know that you can do all of this stuff. So I'm hoping that you guys are somewhat convinced that you can start with any Boolean expression and convert it to a CNF. Yes? Okay. But this also shows you that you can actually validate your own answer with your homework assignment the same way. So I'm going to rename this spreadsheet and share that with you. So we'll rename to today's date, 2017, October 11th. Okay. And click share. Sharing is caring. There we go. Okay. We'll share to everyone. Click save. Copy. Go back here. And I'm gonna go to announcement. So I'll send it to you as an announcement. Okay. So this is spreadsheet on 10/11. Paste the link here. And save. There we go. So if you guys want to play with this or change this to suit your homework assignment, you can make a copy of that first. Just make a copy of this into your own Google Drive, and then you can make changes to it. Alrighty. Cool. Are there any questions about the homework assignment? I think the homework assignment is not as involved as this one, but I could be wrong. It's about the same?
I'd say it's not as involved
Okay.
as this one.
Yep, go ahead.
Close.
Quick question.
Yep.
When you're evaluating, you can, like you did in this example here, you can get rid of the implication first, right? You don't have to work
Yeah.
at the top level.
Oh yeah, but but for people who want to follow step by steps, instructions, they can do it that way. But if you use Boolean algebra and you know your Boolean algebra, you can just apply the rules in different orders. Yeah, because the eventual, what you really want to end up with is a CNF. So however you do to end up with a CNF is okay. It's just that some people might want to have a more procedural approach to this, and some other people know, okay, I know what to do. I can do it in any order that I want. Okay, very good. So any other questions about the homework assignment?
It's due Monday, right?
It is due on the 16th, and I think that is the Monday. Is it?
Yeah.
Okay, let me check.
Today's the 13th. So
It is due on the 16th. And the 16th is the Monday? Doesn't sound like a Monday to
2
me.
days left in the week, 2 days left on the weekend, 5 days on Monday.
Okay. All right.
So I need something.
Any other questions? Yep.
So I ended up with the variable or variable, the same variable, is that fine?
If it is a CNF, it will still be okay, but you can simplify if you have the same variable in the OR. Is it one negated and the other one not negated? They're identical. Then you can just combine them 2 to 1.
That's still valid for CNF. Is that still valid for CNF?
It will still be a CNF if you have 2 variables. Mention of the same variable twice inside the disjunction, it will still be a CNF. Yep. All right. So where is this all going? Okay, now that we know CNF, we can convert anything into a CNF. What do we do with this? Okay. So now we go to this example here. So this example is the one that we already just worked with. Okay, in case you do not recognize this is something that we just worked with. Obviously, this part is wrong, because this last part should be gone. So let me change that first, because I don't want to use a bad example here. So express as a CNF. Okay, there we go. I'm just looking for, there's only one place, which is good. So we just get rid of that last term.
I think you have another reference to the
Yep, I probably do. But I have to get rid of that here too. Okay, so that's that. And then we have this one. But that one may not resolve anymore. So let's see, we get rid of this. And it does not rely on that one to resolve, so we can get rid of that in fact. There we go. Regen. Oh, I forgot that there's one V that I did not fix, right? There's one V that is not backslashed. Okay, so this is the really cool thing of VI is I can look for patterns. I can look for the pattern of V but not preceded by a single backslash. So to do that, I think you just need to do the square bracket and use a caret at the beginning to mean the negation of whatever is following. And then you specify, let's see, I probably need to escape a backslash with a backslash and then V. There we go, we found, oh, big V is okay. Big V, here's the one, there we go. Might as well fix that too. I have used VI for about 30 years, so you know. So I probably use about 5% of the features as a result of using it for 30 years. Wow. There we go. So I think we got everything fixed. Let's check out the example here. There we go. Okay. So psi is still the same thing that we worked with a little bit earlier. Okay, this is what is given to you. Okay, don't ask me why, but this is true. This is in iota, but this is in the iota of the general Boolean algebra type of propositional logic. If you are going to use resolution, you have to first convert it to this. But we already used the spreadsheet to show that these two expressions are really the same. Okay, you know, when one is true, the other one is true. When one is false, the other one is false. So we can use this as instead of the original form. The theorem, the first theorem that we want to prove is this. So proof by contradiction means let's negate it first. So when you negate phi, you end up with this, and then we apply the definition of implication, and then we simplify, and then we use De Morgan's law. I'm looking at this and go like, did I make a mistake here? In fact, I did. There should be three. There should be a triple negation here. It doesn't change the end result because it is still not resolvable, but the note is wrong. And to look for this one, we should be looking for that indication. Okay. Yep, there we go. So the negation, this becomes the negation of the first part or P. That part is right. But this one should be a triple negated, which ends up with one single negation left over here, which also means over here we need that single negation here. Okay. Of course, this one needs to be non-negated. Apologize for all of these mistakes that needs to be fixed. Okay, there we go. All right, so it is still kind of the same thing. You know, it doesn't really change the point that I need to make here, but because when you look at the negation of the theorem as a CNF, it becomes this. Okay, this derivation is correct. And then you join the two CNFs together. the first CNF is coming from the iota, okay, things that you know to be true. The second CNF is the negation of the theorem that you're trying to prove. So this becomes the actual CNF that we want to do resolution with, but there's nothing to resolve here. Because to do resolution, you need one side to have a variable, the other side to have the negation of the same variable. Yep?
Doesn't that single not P get rid of the other two not P's?
Yeah, but that's simplification, it's not resolution. So in other words, this means the same thing without that simplification, but the point is I cannot resolve anymore. So if I cannot resolve anymore, what is that telling you about the theorem? It is not a theorem. Okay? It's not necessarily the theorem is false, it is just that it is not a theorem. It doesn't follow from what is known to be true. Okay? All right, so then we are running out of time, but the other one does work. So the other one does work, that's actually resolvable, and we can resolve to contradiction or false at the end. So that's the end of today's lecture. So please read at least up to what we have here and try to understand the big picture first instead of the detail first.